Thank you. Oh, sorry. Good afternoon, everyone. Today I'm going to talk about our work, the inflection point hypothesis, a principled debugging approach for locating the root cause of a failure. And this is a collaborated work with my colleagues from University of Toronto. As programmers, we all know that debugging is costly. Studies have repeatedly shown that debugging costs 50% of the time and billions of dollars each year. The major goal of debugging is to first locate the root cause. And this includes two steps. First, given a bug report, developer typically needs to understand the failure so that she can reproduce it. Then she further needs to locate the root cause. And there's a large body of work focusing on failure reproduction. They use techniques such as deterministic replay, tracing, log analysis, and core dump, and hardware support like Intel PT to reproduce a failure. However, even with the failure reproduced, locating the root cause is still a daunting task. This is because the failure execution trace on real-world distributed systems is really complicated, contains millions to billions instructions. And locating a single instruction that is the root cause is like finding a needle in a haystack. And in this work, we're focusing on automating root cause localization. We assume that the failure is already reproduced, and we want to automatically locate the instruction that is the root cause. Most of the existing techniques for root cause localization adopt a probabilistic approach. They instrument the program to record predicates such as whether a branch is taken. And then they run the instrument program to collect a large number of successful executions and failure executions. And finally, they find the predicate that has the strongest statistical correlation with the failure symptom as the root cause. However, their result is also fundamentally probabilistic. It could be the manifestation of the root cause, such as an error symptom, that happen to occur together with the failure symptom. And in addition, it requires a large number of failure executions, and it does not provide the execution context that tells developer why the execution reached the root cause and why the root cause, in the end, manifested into a failure. And in this work, we develop an analytical approach that systematically searches for the root cause. The key question we ask ourselves is, what is the fundamental property of root cause that allows us to build a tool to automatically search for it? And this is not an easy question. In the next few slides, I'm going to talk about the reasoning steps that eventually lead to an answer. The first question is, what is the root cause? We borrow a widely adopted definition from the field of quality control. Root cause is defined as the most basic reason for a failure, which, if corrected, would have prevented the failure from occurring. And then we adapt this definition to a software context. First, the root cause is an instruction in the failure execution, which, if changed, would have resulted in a correct execution. However, there could be multiple such instructions, and this leads to the second constraint. Root cause has to be the most basic cause of the failure. Consider this simple failure example caused by data race. Each node represents an executed instruction, and here instruction is an abstract concept. It could refer to Java bytecode instruction, or assembly, or high-level instruction. And the time order of executed instructions is from top to bottom. In this case, we have two threads executing concurrently. They have a shared variable A. And the blue thread sets A to be 0, and later it expects it to stay at 0. Otherwise, it will fail. Now, if the red thread 1 modifies A between the write and read instruction in the blue thread, it will fail. According to our definition, A equals to -1 in thread 1 is the root cause, because we can change the order of the instruction to schedule it after the blue thread reads it and avoid the failure. However, there can be multiple such instructions. For example, if the first instruction in the red thread is a branch instruction that checks a configuration parameter, and we could also change this instruction to avoid the failure by changing this configuration parameter to disable the subsequent execution from thread 1 and avoid the data race altogether. Intuitively, the assignment instruction a equals -1 is a more basic cost comparing to disabling the configuration. Now with this definition, we could introduce the inflection point hypothesis, which provides the property of the root cause that enables us to systematically search for it. First, we linearize the concurrent executions by taking the total order of all the instructions from all the threads and processes into a single execution trace. And clearly, in practice, we cannot possibly linearize all the instructions. Later, we'll talk about how we solve this in our practical tool. Now we explain what is an inflection point. Given a pair of failure execution EF and a non-failure execution EN, their inflection point is the first instruction in the non-failure execution EF that differs from the instruction at the same point in EN. Here is a linearized trace of a non-failure execution that schedules the assignment A equals -1 after the read of A. And given this pair of EF and EN, their inflection point is A assigned by -1 in the failure execution. Because before this instruction, all the previous instructions are the same and are in the same order. And we call the instruction sequence up until the inflection point their common prefix. Next, we define sigma n to be the set of all possible non-failure executions. This includes all non-failure executions that can be generated by different input, and as well as all possible timing orders of instruction sequences produced by the same input. And the inflection point hypothesis states that the root cause is located at the inflection point between the failure execution EF and the non-failure execution EN from sigma n that has the longest common prefix with EF. Theoretically, there are infinite number of non-failure executions, and the one that we are interested in is the one with the longest common prefix. How are we going to find this EN? We're also going to address this later in our practical tool. In the previous example, for the non-failure execution EN prime, if the configuration is changed and the subsequent instructions from red thread are not executed, then their inflection point is this configuration check instruction, because the branch variable has different values between EF and EN prime. However, because we can find another non-failure execution with a longer common prefix, the previous inflection point at the configuration check instruction is not the root cause. On the other hand, we cannot further find another non-failure execution that has an even longer common prefix than this EN, because once A equals -1 is executed at this point, the execution will end in failure. However, identifying what is the root cause can be subjective. This is why we call it an hypothesis. The inflection point hypothesis enables us to build a tool called Carox. It finds the root cause by systematically constructing the non-failure execution EN that has the longest common prefix with the failure execution. But the inflection point hypothesis is a theoretical idea. There can be infinite number of such non-failure executions. How do we find the single one with the longest common prefix? Carox adopts a couple of new ideas. First, we use existing unit tests of the target system as building blocks to construct this EN. We also need to stitch multiple unit tests together to construct this EN. This is because each unit test typically only executes one user operation. Yet, for EN, it often requires multiple operations. In addition, Carox may also need to modify the unit test to construct a non-failure execution with a longer common prefix. The modifications include modifying parameters and scheduling. This ensures that the modifications will always result in a valid execution that can be reproduced by a unit test. And the modification attempt stops when any longer common prefix would end up in failure. In our previous example, further changing this execution EN to get a longer common prefix will have to include A equals -1 between the write and read in the blue thread. Thus, it will result in failure. And Carox stops here. Also, it's not possible to record the total order, and it's also not necessary. Character only takes a dynamic slice from the failure execution, which is a partially ordered trace that contains only the instructions that are relevant to the failure symptom. Given the existing unit test and one single failure execution EF as input, Character is able to construct a non-failure execution EN that has the longest common prefix, and consequently infers the root cause being the inflection point between EF and EN. And Character also outputs the steps to reproduce this EN, so this EN will be useful for developers to understand the failure and the root cause. And now let's see how Character works on a real-world HDFS failure. In this case, the user repeatedly experienced that HDFS master node freezes. And this is the highly simplified code snippet. The symptom occurs in the replication monitor thread. It checks any blocks that are under-replicated and puts them into a needed replication queue. And for each block in this queue, it calculates how many number of replicas are needed. Inside this inner loop, it enumerates nodes from the cluster and checks if the node's capacity is larger than the block size. If so, it will replicate the block and decrement the number of needed replicas. In normal cases, after this loop, the number of needed replicas should be 0. If not, it will throw an exception. In this failure, there is a data race. There's another thread, delete block thread, that is executed whenever the user is deleting a block. It first sets a block size to be the max of long before it deletes it from the needed replication queue. If a user attempts to delete a block that happened to be in the needed replication queue, we can have a data race between line 16 and line 6 if line 16 occurs before line 6. Then the check on line 6 will always fail on all nodes, leading to an exception being thrown. On a large cluster, enumerating all nodes in the inner loop at line 4 can take a really long time. And in the meantime, the needed replication queue keeps growing, causing the master to freeze. You might think this is an easy bug. However, it is not. For any failure, once you know the root cause, it always looks simple. In this case, the failure propagation is actually long, and there are numerous possible branch conditions that could lead to this exception just in this inner loop at line 4. Some are really complicated checks against HDFS replication policy. And the check against the node capacity at line 6 is only one of them. And fail on any one of the conditions could lead to the exception. And developer had a really hard time figuring out which was the cause. Also, the replicate block function consists of hundreds of lines of code between the start to this exception. And that's not even counting the code in the libraries. Not to mention that on the HDFS cluster, there are hundreds of other threads running concurrently. So although the developer can repeatedly reproduce it, he ended up performing numerous rounds of printf debugging, waiting for the problem to reoccur, and only to find that his previous guesses was wrong. In the end, it took him a month to finally find the root cause. He was so frustrated that he wrote a long blog describing his frustrating debugging experience. Now for Character, it only requires one single run, and it can pinpoint the root cause of the failure. First, Character uses dynamic slicing to remove all the irrelevant threads and the irrelevant instructions. And in fact, even for the other iterations of the loop at line 2, which process other blocks from the needed replication queue, Character can remove them from the dynamic slice because they are irrelevant to the failure. Then, Character starts the replication monitor thread that contains a symptom, and it finds there's a unit test that exercises this replication monitor thread. It's called test change code rep. This test creates a file with 3 replicas, and then increases the replication factor to 5, and so that HDFS can replicate it. However, Character finds that this unit test does not exercise the delete block thread. That's also in the dynamic slice. So Character searches for another unit test that exercises this delete block thread. It combines them together to form a new test. And Character further enforces the same timing order when executing this combined unit test. to be the same as the failure execution as much as possible until it results in a failure. In this case, it concludes that the root cause is at length 16 because it's able to construct a non-failure execution that matches all the instructions in EF before length 16. However, once length 16 is included, the failure becomes inevitable. We evaluated Charax on 10 cases. We also manually inserted nozzle operations in 1 case. And the result shows that Charax is able to successfully find inflection point for 7 out of the 10 cases. And the reason for the 3 unsuccessful cases is that there is simply no unit test that exercises the required operations. For 7 cases where Charax is successful, it significantly reduces the number of instructions from millions or billions to 300 in a dynamic slice. Here, an instruction refers to a Java bytecode instruction. And the longest common prefix found by Charax on average contains 165 instructions, indicating that Charax analysis is deep to match a long prefix. And Charax was able to combine multiple unit tests for many of the failures. For related work, due to time limits, I refer you to our paper. To conclude, in this work, we propose the inflection point hypothesis that transforms root cause localization into a principled search problem. We further designed and implemented Charax that turns the hypothesis from a theoretical idea into a practical tool. And we show that it is effective to debug some of the most complex distributed system bugs. And thank you. I'm ready to take questions.
Hey, so I'm Chinmay from Utah.
Can you speak up a bit, please?
So I'm Chinmay from Utah.
Hi.
I loved your talk. Great idea.
Thank you.
So when you spoke about unit test stitching, were you talking about stitching together unit tests and running them on the same thread or
Yes.
across threads? And then how do you figure out which unit tests to choose and what order to stitch them up in?
Yes, thank you. So the question is, how do we combine multiple unit tests together to form a one unit test?
Yeah, and how do you figure out what order to combine those unit tests in?
Yes. So, for example, in this case, we start with the unit test, the first unit test change code wrap, because we first started with the replication monitor thread, and this thread is executed in the test in the first unit test. And then what Charax does is that it follows the dynamic slice to find that delete block thread is not covered in this unit test.
Okay.
So Charax only tries to find in which unit test is this thread executed, and it finds that in test remove, it executes this thread.
Okay.
And this thread is triggered by one of the operations in this test remove unit test, which is the second one, delete file.
Right.
And then after that, Charax just takes this one operation and combine it, put it in this test change code wrap. Mm-hmm. And then we use heuristics to try to make sure that the objects that these operations operate on are the same.
Okay.
And then we try to enforce the timing order.
Awesome. Okay. Thank you.
Thank you.
I believe you came in first. But yeah, go ahead.
Okay, oh, that's me? Okay, Jason Flynn from Facebook. So my question has to, first of all, I really like the framework that you have of thinking about root cause analysis. My question specifically has to deal with dynamic slicing. So there's an important class of bugs that are instructions that never happened.
Yes.
Right?
Yes.
And those would never be captured in a dynamic slice, and you need static analysis to capture those, I think.
Yes.
How would you deal with those? Is there something you can say about those?
Yes. So thank you. So the question is, when we do dynamic slicing, for example, in this case, a dynamic slice actually, if you start with that not enough replica exception, and if the decrementation of number of needed at length 8 is never executed, so this inner loop is actually not on a dynamic slice. And the way that we handle this case is that first we found that there is a unit test change code wrap that exercise this replication monitor thread. And when we compare them, we found that although this decrementation of number of needed didn't happen in the field execution, but it happened in the non-field execution, which is this unit test. And we found that the reason that in this unit test change code wrap, the failure didn't happen is because this number of needed is decremented. So that's how we found that, okay, this event that actually didn't happen in the field execution is related to the failure. It's because the unit test avoid the failure because this instruction happened.
So the secret sauce is you do dynamic analysis over all the unit tests in addition to the failure executions.
Oh, sorry. Then I didn't make that clear. So the sequence is we do dynamic slice on the field execution, but we don't do dynamic slice on the unit test because there's no symptom to start with. And we compare the dynamics. We use a dynamic slice to compare against the full trace of unit tests.
One more quick question.
Jeff Kenning, Harvey Mudd College. So you're finding you're finding the root cause there where the variable is set incorrectly, but at least in a complex example like the one you're showing on the left, that might be checked in a number of places. Do you give any help to the developer in finding the other half of the root cause?
Excuse me, can you repeat the question
Yeah.
again?
So in general, here you've got a very nice thing that on line 16, size is set wrong. On line 6, size is checked and fails. But in a complicated program, size might be checked 10 different places, and all of them might lead to this to an exception. Do you give the developer any help in finding the other side of the failure, where it's checked?
So yeah, just to make sure that I understand the question. So you're saying that it's possible that in this replication monitor thread, there are multiple places that checks the size of the block.
Yeah.
And they are all relevant to the failure symptom.
Yes.
So in that case, how our tool works is that we will be able to find the last one in these multiple conditions that would result in the failure. And we will consider the last one and tell developer when the execution reaches this point and the block size is wrong, then the failure is inevitable. Then developer will use this as a root cause to fix the failure. If after this fix is still the execution still fails, then Carix will, in that case, Carix will be able to find the earlier conditions.
Okay, thank you.
All right, let's thank the speaker again.